Hi everyone, and welcome to the flipped recording today for 3.06, a balancing act. Be sure to take notes during this recording. Balancing chemical equations is one of the hardest things that you'll do in the chemistry unit. So you want plenty of examples of different equations so you can refer back to those as you take your quiz and your test. Remember, you also want to update your slide or your notebook paper page with the lesson number and the title. So if we're looking at the slide up here, you want to change this the number and the lesson title. It's 3.06, a balancing act. Make sure you get all those guiding questions in, and then over here, this would be a great place for you to put some of those examples in that we'll cover in the lesson. So in the lesson content today, sorry, I'm trying to adjust this bar down. And it's not going to do it, so we'll just leave it there. For the balancing act, we're going to get into the lesson introduction. And if you take a look, the law of conservation of mass is very strict. It must be obeyed in all chemical reactions. Chemists can obey this law by balancing the chemical equations that represent various reactions. In this activity, you will practice balancing equations, which you learned about previously. This skill is very important to succeeding in chemistry. The more you practice, the easier it will become. And you can probably hear my dog snoring in the background. So remember, you don't need your lesson goals, and there's no new vocabulary today. So we'll go on and just make sure we only have 2 guiding questions to answer. Why is it important to balance equations, and how do scientists predict how much of a product can be formed? So I'll just take a little screenshot of these. That way we can refer back over to that as we go through the lesson. All right, so question 1 for the guiding questions is answered right here. Why is it important to balance equations? It is necessary for all chemical equations to obey the law of conservation of mass. It's also important for you to write down what that is. So this law states that that mass cannot be created or destroyed in chemical reactions. So this means that the amount of each atom at the beginning of the equation must equal the amount of elements at the end of the equation. So how can you tell if an equation is balanced? You can count the number of each element on the left side of the arrow. Remember to consider the subscripts for each element. A coefficient in front of the molecule means that there are that number of molecules. So you multiply the coefficient by the number of that element in the molecule. Next, you want to count the number of each element on the right side of the equation. And if there are equal numbers of each element on both sides for all elements in the equation, it is balanced. All right, so a balanced equation has equal numbers of each type of atom on both sides of the equation. In this modeling activity, circles represent atoms of hydrogen and oxygen. You're going to use the atoms to balance this chemical equation. H2 plus O2 yields H2O. So you can create a model of molecules by overlapping the hooks between the atoms. To unhook the atoms, the 2 atoms, you select and drag where the hooks overlap. So if we have 2 H's, H2 and O2, and then that yields H2O. So you're able to build more H2, and then you can connect with it's called these little hooks. So we can put this one here, and this one, we got into this lesson before, you kind of have to spin them around so it looks like this. All right, so how do your models look? You should notice that there are equal amounts of hydrogen atoms in the hydrogen molecules as in the water molecules. So there should be an equal number of oxygen atoms in the oxygen molecules as in the water molecules. This proves the law of conservation of mass. If you did not have an equal number of each color of atom, try the activity again. So remember, you use those 4 steps to balancing equations. And we will go back and look at that. We just were hooking the atoms together there, but if you notice when we go back, I don't know if it'll reset it for us. It might. It did. So we were building this side of it. We had 2 hydrogens and 2 oxygens. So if we build that out over here, we notice that over on the other side, on the product side, I mean, that there was only 1 oxygen and 2 hydrogens. So in order to balance that equation, you're going to have to add a coefficient in front of that H2O water molecule in order to balance that out. So what it ends up looking like, you have H2 plus O2. So building this takes a little longer than actually just being able to write it out. So this is a very visual way of seeing that. Okay, so this is what we're starting with. And then what we're ending with is these 2, which we kind of built a while ago. Okay, so as you can see, we're short over here. We only have 1 red and 2 reds over here. So like I mentioned, if you add the coefficient 2 in front of the H2O, that then gives you 4 hydrogens and 2 oxygens. So then we've got to go back over to this side and put a 2 in front of this hydrogen so that we would have 4 over here and 4 over here. So what the final product would look like for it to be balanced would be, you've got 2 sets of H2. So that would be 2 H2 plus O2, right? And then we've got 4 H2s. No, what did we put a 2, not a 4? Sorry about that. Yeah, we put a 2 in front of there. So that gives us 4 hydrogens. So it's basically building another one of these. And another 2 oxygens. So let me get these 4. So this is what we had. We're moving it out of the way. And this is what we have at the end when it's balanced. So again, you would want to build these, together like this because they are bond. You're showing it. You would have 2 water molecules. So we would add that other oxygen. So again, that's what we started with. That's why it's out of the way. So at the end, you can see we still have 4 hydrogens, 2 oxygens, and this is the beginning, 4 hydrogens and 2 oxygens. All right, so as you go through, if you're checking your model, this is a pretty difficult way to teach this concept. So you notice that there should be an equal number of oxygen atoms and hydrogen atoms. So we did that, and that proves the law of conservation of mass. So if you did not have an equal number, then remember you have to go back and do those steps. So we know that balancing reactions and the law of conservation of mass is important, but how useful is it? So chemists in the industry use balance equations to predict the amounts of products formed or reactants needed for a reaction. By knowing the masses of the starting material and a balanced chemical equation, a chemist or an engineer, or even better, a baker, could predict how much of a product could be formed. So a baker uses balancing. You might not think if you're wanting to be a baker that you have to have a chemistry background, but absolutely. In this case, a recipe represents a balanced chemical equation. So the ingredients are the reactants and the brownies or the other baked goods are the products. And if a baker only has 6 eggs, he can determine how many cakes he can make using a recipe, his balanced chemical equation. So chemistry can be delicious. So in this lab, you used models to show how to balance chemical equations. And it's important to balance those chemical equations so that they agree with the law of conservation of mass. So answer these questions to explain the law of conservation of mass. What is the law of conservation of mass? We saw that earlier. It states that mass cannot be created or destroyed in a chemical reaction. And then in chemical equations, this means that there must be equal amounts of each element on both sides of the chemical equation. And then how do you balance a chemical equation? You count the number of each element on each side of the equation, and then you place a coefficient in front of the chemical formula to add more of an element. You repeat this process until all elements are equal on both sides of the reaction. So guiding question 2, how do scientists predict how much of a product can be formed? We talked about that on the last slide by kind of looking at those outcomes and doing that math. And I also want to show you another way to balance equations, maybe a little more visual than the model in the lesson. So I'm going to pull that PowerPoint and show you that. Okay, so pulled this PowerPoint up. I used it in a live session the other day. So if you're able to go look at that recording, great. This came out of our content that was before this has been modified. So this was a couple of years ago, but I think the visual on it makes it a little easier. So basically it shows that you write out the chemical formula, the equation that you're trying to balance. And so here you can see aluminum, chlorine, potassium, yields aluminum and then potassium chloride. So the one easy way is this dot method that we're looking at. So aluminum, it shows there's 1 because there's no number beside it. So we know we just have 1. And then the chlorine, this is Cl. Remember that it's always going to be a capital and a lowercase letter, and that 3 means that we have 3 of them. We have 1 potassium, and then it yields aluminum, potassium, and chlorine. So this is a very easy way to see that immediately we know the chlorines are not matched up. So these steps, I think, the 4 steps they mention in this lesson, kind of written out here. You write the chemical equation with the symbols. Step 2, count the number of atoms of each element on both sides. So you may put this method in your notes along with this picture and draw that out, that problem, so you're able to see how to do this just another way. Step 3 says balance atoms using the coefficients. So that's where you have to put a big number in front of the molecule or the element compound. So from there, we'll make sure the equation is balanced. So if we look at that, we can see that chlorine, again, is not balanced. So we want to add a 3 in front. Okay, and when we do that, because we're not able to just come over here and add a tiny 3, we're not able to do that. We have to add a coefficient. So that gives us 3 chlorines, but it also gives us 3 potassiums. So then this step's already done for you, but we know we only had 1 over here before. So if we put a 3 in front of it, then that gives us 3 potassiums as well, and now the formula is balanced because you're able to see 1 aluminum, 1 aluminum. Remember that this arrow in the middle is kind of our reference guide. The chlorines 3, 3, and potassium 3 and 3. So hopefully that example is helpful in allowing you to see another way to do it that you may write out on paper, since that simulation in the lesson doesn't really do that. And then from there, you'll have a couple of those type of examples you can put in your notes, and that should help as well. So as we wrap up, if you have questions over anything, you need help, please come see me in Help Lab, and have a great day.